Good morning. So today we will see some more problems. Today first we will see the problem based on the superposition theorem. Here in this problem we are asked to determine the current flowing through this 4 ohm resistor in the presence of both the sources of EMFs E1 and E2 when are acting simultaneously. So to find out the resultant current flowing through this resistance R2 in the presence of both the sources of EMFs, let us use the superposition theorem. And according to the superposition theorem, we have seen that the net current flowing through a certain component is nothing but the algebraic sum of the currents flowing through that component due to the individual sources. That is the algebraic sum of the currents due to the individual sources. And while obtaining the effect of an individual source, the other sources should be killed for their EMF, retaining their internal resistance in the circuit. So, let us first obtain the effect of the first source of EMF, E1. Step 1. To find the effect of E1 till E2 for its EMF, retaining its internal resistance in the circuit. Retaining its internal resistance in the circuit. So in this case, no internal resistance is mentioned here, so we can consider the internal resistance of the source E2 is 0. So if the source E2 is killed for its EMF, then the network reduces to the form E1 R2 and R. This is R1, R2, R3 and E1. So to find out the current flowing through this resistance R2, first we have to obtain the total current I flowing through the circuit, or the total current I drawn from the source E1 when E2 is killed for its EMF. So in order to find the total current I drawn from the source E1, we must first know what is the total resistance of the circuit. The total resistance R of the circuit is nothing but equal to R1 plus R2 parallel R. Here R2 and R3 are connected in parallel, and this parallel combination of R2 and R3 is connected in series with R1. So here the total resistance of the circuit R is equal to R1 plus R2 parallel R3. So the parallel combination of R2 and R3 is connected in series with R3. So using the values of R1, R2 and R3 here, we get R1 is 2 ohm plus R2 parallel R3 is 4 into 2 divided by 2 plus 2. So this is equal to 2 plus 8 by 6. So this is 2 plus 4 by 3, or this is equal to 10 by 3 4. the total resistance R of the circuit works out to be equal to 10 by 3 ohm. And once we know the total resistance of the circuit, now we can find the total current I drawn from the source E1 by the circuit. So I is equal to E1 upon R. So E1 is 10 volt divided by R is 10 by 3. So the total current drawn from the source is 3 ampere. So then this total current of 3 ampere arrives at the junction P. Certain part of the current flow through R2 and the remaining current flow through R3. So let I1 is the current flowing through this resistance R2 due to E1. I1 is the current flowing through R2 due to E1. So this part I1 is equal to, by using the current division formula, we can express it as R3 upon R3 plus R3 into R, the total current drawn from the source E1. So R3 is 2 ohm divided by 2 plus R2 is 4 into 3 amperes. So this is equal to 6 divided by 6. So it is 1 ampere. So the current flowing through this resistance R2 due to E1 works out to be equal to 1 ampere, and this current is found to flow from the point P to the point Q, that is in the downward direction. So I1 due to E1 is 1 ampere from P to Q. So remember this. So this current through the resistance R2 due to E1 flows from P to Q, and this current is about 1 ampere. So this is the first step. Now in the second step, what we need to do is we have to find the effect of E2. So step 2 is to find effect of E2 in E1 for its impedance, retaining its internal resistance in the circuit. The network we get will be of this type. This is R1, this is R2, this is E2, this is R, E2, R2, R1, R. So this source E2 will send the current in this direction. Say R is the total current sent by the source E2 in the circuit. This is the junction P, this is the junction Q. At the junction Q, certain part, say I2, flows through R2 and the remaining current flows through R2. So we want to find out this current I2 flowing through R2 due to E2, and for that purpose we have kept the source E1 for its EMI. So in order to find the total current I drawn from the source E2, first we must know the total resistance of the circuit. The total resistance R of the circuit is equal to R3 plus R1 parallel R. The parallel combination of R1 and R2 is connected in series with R3 across the source E2. So this is R3 is 2 ohm plus R1 is 24 divided by 2 plus 4. So this is equal to 2 plus 8 by 6. So this is 4 by 3. 4 by 3 is 10 by 3 ohm. The total resistance of the circuit, work circuit, equal to again 10 by 3 ohm. And if this is the total resistance of the circuit, then the current I drawn from the source E2 by the circuit will be equal to E2 upon R. E2 is 20 volts divided by R is 10 by 3 ohm. So this works out to be equal to 6 ampere. This works out to be equal to 6 ampere. So the current drawn from the source E2 is equal to 6 ampere. So out of this total current I drawn from the source E2, certain part I2 say goes through R1 and the remaining current go through R1. Therefore, the fraction of the current flowing through R2 due to E2 is equal to R1 upon R1 plus R2 into R, the total current drawn from the source E2. So R1 is 2 ohm divided by 2 plus 4 into 6 ampere, the current drawn from the source E2. So this is equal to 12 by 6. So this is 2 ampere. So the current drawn from the source, the current flowing through this resistance R2 due to E2 works out to be equal to 2 ampere. So this current I2 equal to 2 ampere flows from Q to P. This current is going to flow from Q to P. So the current through this resistance R2 due to E1 flows from P to Q, and the current through this same resistance R2 due to E2 is going to flow from Q to P. So this is I1 and this is I2. So what will be the net current flowing through this resistance R2? Therefore, net current flowing through R2, that is 4 ohm resistor, is I2 minus I1, because I2 is greater than I1. I2 is greater than I1, so it should be I2 minus I1, and I2 is 2 ampere minus I1 is 1 ampere. So the net current flowing through the resistance R2, that is 4 ohm resistor, will be equal to 1 ampere, and this current will flow from Q to P. This current will flow from Q to P, that is in the upward direction. So this is the first application of this superposition theorem to determine the current through a certain component of the given circuit by using the superposition theorem. So that is about this problem. So next we want to see is the application of the maximum power transfer theorem. So let us see. So here we have the next problem dealing with the maximum power transfer theorem. So for a given circuit, you are asked to calculate the value of RL, for which the power dissipated in it will be maximum. Also, you are asked to find out what is the value of this maximum power that will be dissipated in this load resistance RL, or what will be the maximum power that will be available across this load resistance RL. The first question asked is when this power will be maximum And the second question asked is to find out what is the value of this maximum power available across this load resistance. So here we have the given network connected to the left of the terminals A and B, and to the right of the terminals A and B we have a load resistance R. So in order to find out what should be the value of RL for which the maximum power is available across this load resistance, we must first find out the internal resistance of this source. Or in short, we have to first Theoremize the given network, and obtaining the Thevenin equivalent circuit for this network, we can know that what should be the value of RL for which the power available across this load resistance will be maximum. So let us first obtain the Thevenin equivalent circuit to the network to the left of the terminals A and B. And for that purpose, we have to follow these 4 steps. So in the first step, what we need to do is remove load resistance from A and B. And if we remove the load resistance from the terminals A and B, the network we get is of this type. These are the terminals A and B. This is the resistance R1, this is R2, this is R3, and this is R4. Now, for this network, what we have to do is we have to obtain the Thevenin equivalent circuit for this network. What we need to do is we have to obtain the values of VTH and RTH. What is VTH? VTH is nothing but the open circuit voltage across the terminals A and B, and RTH is nothing but the equivalent resistance of the given network when viewed backwards from the open terminals A and B, when all the sources of EMFs in the given network have been replaced by their internal resistances. So let us first find out the value of VTH. So to find out the value of VTH, this open circuit voltage VOC is nothing but equal to VTH, and this open circuit voltage across terminals A and B is nothing but the potential drop produced across this resistance R1. It is nothing but the potential drop produced across this resistance R1. So to find out the potential drop across R2, first we must know what is the current flowing through this resistance R2. So that I is the current flowing through this resistance R2, and this current R will be given by R is equal to E upon R1 plus R. So E is 18 volt divided by R1 is 3 ohm plus R2 is 6 ohm. So 18 upon 9 is 2 ampere. So the current flowing through this resistance R2 is 2 ampere. So knowing the current flowing through this resistance R2, we can find out the potential drop across R2. Therefore, ED across R2, which is nothing but equal to VOC, and hence this is nothing but VTH is equal to I into R2. I is 2 amperes multiplied by R2 is 6 ohm. So I is equal to 12. So the value of VTH works out to be equal to 12 volts. So you can get VTH is equal to 12 volts. This is the value of VTH. Now, in the second step, we want to obtain the value of R equivalent or RTH. In step 2, we have to find out the value of R equivalent or RTH. So in step 2, to find R equivalent will source of EMF for its EMF. So we have to remove this source of EMF from the circuit. We have to keep it for its EMF, retaining its internal resistance in the circuit. No internal resistance is mentioned here, so we can consider it is equal to 0. And when this network is viewed backwards from the open terminals A and B, that gives the equivalent resistance of this network, and this equivalent resistance is nothing but the value of RTH or Thevenin resistance. So here R equivalent will be equal to RB plus R1 parallel R2. R3 plus R1 parallel R1. This is the equivalent resistance of this network. So using the values of R1, R2 and R3 here, we get R3 is 4 ohm, R1 is 3, R2 is 6 divided by 3 plus 6. So this is 4 plus 18 by 9. So this is equal to 6 ohm. So R equivalent is 6 ohm. Therefore, RTH, the Thevenin resistance, which is nothing but equal to R equivalent works out to 6 ohm. So once we know the values of VTH and RTH, then we can draw the Thevenin equivalent circuit. Then we can draw the Thevenin equivalent circuit. So in step 3, we can draw the Thevenin equivalent circuit and find out the value of load current. So replacing the network to the left of the terminals A and B, this is RTH equal to 6 ohm. Yeah. So in step 3, what we need to do is to find I1 plus given network to left of A by Thevenin's equivalent. So we will get the network like this. These are the terminals E and B. This is RE or RTH. This is VTH or VOC. Doesn't matter. And to find out the value of load current, again we connect the load resistance RL in the circuit. To find out the value of RL, we connect the load resistance in the circuit. So when the power available here, we can find out the value of IL. The current IL flowing through this load resistance RL will be given by RL is equal to 3pH upon RIL plus R. Or this is nothing but RTH plus RL. Doesn't matter. You can write it as RIL or you can write it as RTH, RTH. So this is the current flowing through the load resistance RL. Now, if this is the current flowing through this load resistance RL, what will be the maximum power, or when the power available across this load resistance will be maximum? As we know that the maximum power transfer theorem states that the maximum power is delivered from the source to the load if and only if the internal resistance, the value of the load resistance is exactly equal to the internal resistance of the source. So here, since RIL is considered to be the internal resistance of the source. So the maximum power will be delivered the load resistance when RL is equal to RIL. Therefore, RL must be equal to RIL is equal to 6 ohm, because the value of RIL is 6 ohm. So, under this situation, when the value of RL is equal to 6 ohm, the maximum power will be delivered to this load resistance. So, this is in accordance with the maximum power transfer theorem. So, if this is the current and if we substitute value of RIL equal to RIL in this expression, the current I flowing through the circuit will be given by the equation IL, IL is equal to 3pH upon RIL is replaced by RL, so it is RL plus RL, so this is equal to 3pH upon plus RL. So this is the load current IL flowing through this load resistance RL under the condition when the value of this load resistance is exactly equal to the internal resistance of the source. And if this is the current flowing to this load resistance RL, for maximum power to be available across load resistance, therefore now we can find out the maximum power will be equal to IL square into I. The maximum power available across this load resistance will be given by IL square into I. So using this expression for IL here, we get the maximum power. Therefore, P max is equal to IL square will be 3pH square upon 4 RL square multiplied by R. So this IL is replaced by 3pH by twice RL. So its square will be 3pH square upon 4 RL square into RL. Yes. So 1 RL will cancel with this RL here. So maximum power available will be 3pH square upon 4 RL. And now using the values of 3pH and RL, we get 3pH is 12 volt. So it is 12 into 12 divided by 4 into RL is 6 ohm. So this is 3 into 6. So the maximum power available across the load resistance will be equal to 6 watt. Therefore, P max will be equal to 6 watt. So this is the maximum power available across the load resistance. And if the value of load resistance RL is either increased beyond 6 ohm or decreased below 6 ohm, then the power available across this load resistance will be always less than 6 watt. So this is the maximum power available across the load resistance, or this is the maximum power dissipated in the load resistance. So that is how we can find out the maximum power available across the load resistance by using the maximum power transfer theorem. So with that, we close the problems on the chapter here, and next we will start the next chapter. Okay, good.